Hello, and welcome to an example on plastic deformation in your members focused on axial deformation and how to deal with that. So what we have here is a rigid bar that's supported by two rods. The rods have a area of 1.25 inches. They attach to the rigid bar at A and B. We have an unknown uniform load W that's only applied between A and B, so that overhang doesn't matter. And of course, A and B are 8 feet apart, but the rods are 5 feet long, and it's steel, so we have 30 times 10 to the 6 psi for our modulus of elasticity. Well, it turns out that when we put this unknown load W on there, we yield the bar, and it starts deforming, but we unload it after there's been a permanent deformation of 0.15 inches left in the bar. And so what we need to do is find, well, what is this W that yields the bar? And also, what's the total deformation that the bars are going to experience before we unload them? Not just the permanent set, but the total they experience during loading if we know the yield stress of the material is 36 KSI and we can model this as an Elasto-Plastic material. So the first thing always we want to do is a little bit of static. So we'll draw our free body diagram, and it's pretty straightforward. We just have the force at A and the force at B. And again, remember, W only goes between A and B. So that's nice and straightforward. And so when we do our statics, we can just talk about symmetry, and we know that the force at A equals the force at B. And so that's just WL over 2. We don't know W, but L over 2 would give us 4 feet. So right now, we know the force at A and we know the force at B as W times 4 feet. Now, when we want to then continue and start looking at, well, all right, can we say anything about the deformation? Or how can we use that FA or FB value that we got in terms of W and relate that back to the stress? Let's remind ourselves what our Elasto-Plastic stress-strain curve looks like and the behavior that we're dealing with. So it's going to be a flat curve. We're going to peak at sigma yield, which we know is 36 KSI. And we say that we load this, and then at some point we unload, and we're left with this permanent, now on this diagram it's strain, and a yield strain that is an elastic amount that we get back. And of course, we can relate strain and deformation by the yield strain would just be equal to the yield deformation divided by L. The permanent strain is just the permanent deformation divided by L. And we happen to know the permanent deformation is 0.15 inches. And of course, L is the 60 inches, the length of the actual rods. So that's interesting because we can then actually see that the total strain that this experiences is just the accumulation of the permanent strain plus the strain that would take us to yield, or that elastic strain that we recover upon unloading. And we can see that our peak stress really is the yield stress. So we can use this information to determine our deformation values, and we've said the total deformation then should be the yield deformation plus the permanent deformation, because we can see that in terms of strain on our stress-strain diagram. Again, reminding ourselves that strain is just stress and strain are related through L, and of course strain is also stress divided by E. Let's not forget that. And so we can use that to rewrite our expression in terms of the yield stress and our modulus of elasticity E, along with the length 60 inches, add that to our permanent deformation, and we're going to get back out that our total deformation before unloading is 0.222 inches. So interestingly enough, we had about 0.072 inches of elastic deformation that was recovered, that snap back that you get upon unloading. But what that doesn't do is tell us, okay, well, what then is our W load that we're going to have? So to find W, we do want to then say, well, okay, if we know the force in the member and if we know a stress, can't we use our P over A equation? Well, remember, we do know the stress because we yielded, and that's so critical. We know the force in the member. That's going to be FA or FB, and so we can just divide that by the area and set that equal to the peak stress. This only works because we yielded, and in an elastoplastic material, once you're told you're yielded, you know the stress. I cannot emphasize this enough. So we can set our FA over A, which our FA term has that unknown W in it. We can set that equal to the yield stress of 36 KSI. And so we can see our inches will cancel. We're going to get kips per feet, and we actually get that the W is 11.25 kips per foot, and that's the load that caused our bar to yield. So take a little time, study this. Please remember, if you sketch the elastoplastic diagram, remind yourself, what's the total deformation? Where's the permanent set? Where's the elastic recovery? And that once we yield, we easily know what our stress is going to be. Then you can always jump in and solve these problems. Just keep all this in your tool belt so that you can use it later on. Thanks for watching.